All right, good evening, everyone, and thanks you for joining us. I'm going to turn on my video very quickly just before I actually start the presentation. I'm going to turn it off when we present, just so everyone gets a chance to see me. All right, good evening, and welcome to this edition of DC iOS. This will be our first attempt at a virtual meetup, and hopefully it won't be our last until the point that we can actually go back and do meetups in person again. I'm Scott Luxenberg. I'm one of the 3 co-hosts for DC iOS, as well as being this month's presenter. So we don't really have many announcements, obviously, since we're doing this virtually. There's no any sort of on-site business that we have to address. So thanks for taking the time to join us this week. And then, so I will say predominantly we will start off handling questions in the chat. We won't really address questions until the end. Unless if I see something that is very pertinent to what I'm talking about, then I might bring it up at that time. Otherwise, we will get to all questions at the end. We may try seeing if we can unmute people to ask questions, but if not, we'll just predominantly try to handle it in the chat. And yeah, hope everyone has a good time. So with that, I'm going to turn off my video and start sharing my screen. All right, co-host, can you confirm that my screen is sharing?
Yep, looks good.
Alrighty then, thank you and welcome to my presentation, which is called D.F.I.R, the eye of your iDevice, or how I learned to stop worrying and trust that Apple is totally cool recording all my data and is totally safe, right? So to get started, I'll give you a little bit about me. So I work here at Capital One. I've been at Capital One for 2 years. My anniversary actually will be this month, so I'm pretty excited about that. I am the tech lead for Team Scorpion, which is we're part of the Set for Success and Ease Card mobile teams, and we support some of the credit card functionality in the app. And I'm also, as you know, one of the DC iOS co-organizers. On the side, I dabble as a freelance percussionist and a drummer, so you can find me in multiple musical groups throughout the area. You might also find me in a few theater pits. And once in a while, I dabble with robotics. I used to be one of the advisors to the Thomas Jefferson High School in Virginia. I used to be one of the advisors to their robotics team, but they have temporarily shut down for a little while. Not even because the school is being shut down, it's because they decided to take this year off. I'm also a begrudging cat dad or something. I'm coming to possession of a cat through my fiance, and the cat seems to love me now more than anyone else. And an interesting fact about me is I actually do not own any personal Macs or iPhones at home. My personal machines are all Windows. My personal phone is an Android. I just happened to one day fall across a iOS programming class in college, and it turns out I enjoyed it and was good at it. And I'll give a quick warning that there will probably be a lot of bad jokes coming up during this presentation. And now I'm sure you're wondering, okay, I'm looking at this, but why is he able to talk about this? He could just be making stuff up. So before I was at Capital One, there we go. So before I was at Capital One, I spent 5 years as a government contractor. I predominantly supported state law enforcement agencies, and I worked on tools that supported digital forensics efforts. And as I said, my predominant focus was Mac and iOS support, but I also have some experience with Windows, Android, and embedded devices. So now that we get into the first part of the presentation, you're wondering, I threw around the acronym D.F.I.R before. What is that? Is it a type of Swiffer? Is it the name of a cat? Could it be a piece of technology? So D.F.I.R actually is a 4-letter acronym that means Digital Forensics and Incident Response. Digital forensics is the act of performing collection of digital evidence that resides on any and all type of electronic media. An incident response is using that kind of forensics to respond to and analyze threats such as data breaches, malware, hacks. So when you combine the two, you get the act of analyzing data and turning it into something that's actionable. For our purposes tonight, we will be predominantly focusing on the aspect of the digital forensics side, since it's more geared towards our purposes of looking at what's actually on the device, and it's tend to what law enforcement would be looking more at. Incident response is something like a private company will be handling, like, okay, we got attacked, who did it and why. And then again, as I said, incident response wouldn't get into kind of the meaty details we would have where we actually get to talk about the phone structure. Surprisingly, you wouldn't think this, but the digital forensics community is actually very open. So if you ever look up the SANS Institute, they're a major provider of D.F.I.R-related training courses that you can take. I mean, obviously, it's mostly expected you're going to be footed by someone who has a budget because they're fairly expensive. But then, for example, NIST, the National Institutes of Standards and Technology, they have a guideline and results of law enforcement, a lot of different devices, tools, and how they're used, and those are public for anyone to use. A lot of this can be found on open source like GitHub, Medium. A lot of the well-known forensics experts actually keep blogs. And of course, there's plenty of textbooks that you can find. So now, we're going to talk about the eye of your iDevice. So as you would expect, there are about two primary constructs that are used to actually construct all the data sources of all the parts of your phone. Technologically, it's predominantly SQLite database and plist, since this is all Apple devices. And the SQLite traditionally tends to be core database related objects. So like if you ever look at a database, you'll see it matches more of the known core data-like scheme, like Z something, the primary key is ZPK. There's a few exceptions where it's not really core data and it's more of a traditional straight up SQLite database, but in general, it's core data. There are a few exceptions, which I'll kind of get into a little later, but they still tend to be related to one of these underlying aspects. And then again, so I will give the slight forewarning that this is going to be a pretty technical talk, and I don't really mean in terms of the programmatic sense. There's not a lot of code in this. This is purely more on data structures, databases. There's going to be a lot of SQL in here. So this will definitely get into the nitty gritty of what makes up a device. So when you're talking about a device, you got to be wondering, how do I get this out? So there are kind of three ways that are known to people that allow you to get out a device. The first is that the manual method, and that's assuming you have your phone available to you, and you know the password, or maybe you're able to brute force the password. Then you can get in, look at all these different applications, touch around, and then pull up all the data that you want. Usually that's very much the least preferred method, just because it's so much more time invasive. You have a chance of actually ruining evidence on the device because you're actually looking at it. The next way is called a logical acquisition, and that's the most common and accessible way to get large sets off of a device. And with an Apple phone, there's about 3 ways to do it. Using backups, which you can either get from the iTunes backup, or there's some tools that are available either by paying money, or there's 1 or 2 open source tools that I don't think they've been updated in a while. They probably don't work anymore, but you can also, if you know the password, you could actually download the iCloud backup. Or you could jailbreak the device and then relay into it and dump out the contents. Jailbreaking itself has some implications because, again, it's modifying the contents of a device, so it's kind of a gray area, but it's still technically supported. And then the final way is through a physical acquisition, through which either you actually have a device, you pop it open, and you grab out the hard drive and you're going to copy it, or you're able to copy the hard drive through like the USB cable. This traditionally tends to be preserved because it usually has the least footprint touch on a device, because then it's just copying the disk out and then you haven't actually changed anything. Though Apple being Apple, they've made it a little harder with iDevices. There are ways around it, but I'm not going to really go into that in this part at all during this presentation. But there are ways that have been talked about how people can get that. So, and yes, I'm sure you've noticed I've tried my best to be punny during these slide titles. I tried. So with the iOS file system, if you look at it, if you have a full backup, you'll look that it traditionally looks like even a Mac OS file system. You have applications, you have a system folder, you have a library folder, you kind of have the general folders that you'd find on a Unix file system. Though the In reality, the iPhone ignores about 90% of that. It's just there, it's just bloatware because of the OS base, but it's not really factored into. Predominantly, the predominant source of a phone's data comes from a directory called private var mobile, which is considered the iOS's home directory. And this is where the actual sandboxing implications, as you hear, like when people talk about their app is sandboxed, the iPhone is sandboxed, mobile is the home of those sandboxes. There are a few exceptions. Some data can be var and found outside of mobile, like it might be in private var root, private var wireless, private var network D, and private var preferences. However, those can only be gotten through a full disk image or from a jailbroken device. Otherwise, those folders don't exist. They magically don't exist. You have no idea that they're there. So when I talk about some of the file paths during this presentation, if you see the good old Linux home notation, assume home automatically translates to private var mobile. So I will give a disclaimer that the device I used to get all this information was actually a jailbroken device because it was a little easier, but I'm going to talk about so we have the implications on what a iOS and iTunes backup looks like. Again, as I'll state everywhere, everything I'm talking about here is publicly available knowledge. I even researched this myself. There's nothing here that you can't find by doing a quick internet search. And these are all things that have been very well documented over the years. So the iOS backup format has kind of had multiple evolutions. There are 3 distinct states. iPhone OS 1 through about iOS 4, there were about multiple different versions of the manifest.md backup device, backup file. I'm not really going to focus on this because A, that was so long ago, I don't think anyone really remembers it, at least what a backup would look like. And B, it was so fragmented. I think each time there's an iTunes update, the backup format changed that it doesn't really make sense to talk about. The next major era was from iOS 4 to iOS 10, which the backup source was a file called manifest.mdbd, which was abbreviated for mobile device backup database. And then since iOS 10, it's been a file called manifest.db, which is just a SQLite database. And these backup formats, not only being tied to the iOS major versions, they were actually predominantly also tied to the iTunes major version, because iTunes, up until I think really this OS, was the predominant source of actually backing up your phone. It's how you would copy it onto a device. By default, these backups are not encrypted unless it's enforced by like an MDM policy, but they can be enabled. The flag indicating that encryption is actually indicated in a manifest.plist file. When the backup is encrypted, the manifest files are not encrypted. The exception is the manifest.db database is locked. So you can like go look in your iTunes backup directory and you'll see the iOS files. You can see the file structure of the backup, but all the files are basically gibberish. If you do have a password, it's fairly easy to undo this backup, and there are also plenty of tools that do that if you have the password. But as with all things, if you don't have a password, everything is a time-intensive process. So here I've taken some screenshots of the non-source files that happen to exist. So this is both the info plist and the manifest plist. And these are used basically to gather database. So if you look at the info plist on the left, it actually has basically the contents of your phone's device name, its display name, the GUID, IMEI, the time it was last backed up, the product name. So this is all relevant information letting you know about the state of your device. And then on the right is the manifest.plist, which tells you if the backup was encrypted, the backup version, the date of the backup, and then also has the manifest key bag, has some information about lockdown, which I'll get into a little bit. And then you'll see right there, there's a really big dictionary that's 387 items. That dictionary contains lists of all third-party applications, because Apple's own applications kind of fall under a different policy. That application list actually allows you to see all the apps that have been installed on your device. Now I mentioned it, as you can tell by looking at this manifest.plist, this came from a phone that had an encrypted backup, if your backup was not encrypted, this is encrypted value would not be here, as well as neither of these manifest key bag or backup key bags. They would just be gone. They wouldn't need to exist because they're not there. And you also can actually see that if the phone had a passcode set or not. But I think in general, phones really have passcode set nowadays. So now I'm going to kind of get into the structure of the backups. Like, we're not going to spend too much time on these. So I got this screenshot from the iPhone wiki, and it's one of the resources I've listed later at the end of the presentation, because not many people have a device that's older than iOS 10 lying around. So iOS 9, because iOS 10 was the database. So I don't think there's anyone who has these kind of backups stored around anymore. So basically, if you look at it, you'll see that it starts out with the header indicating the MDBD size, as well as a string that basically indicates where the domain is. And as a quick side note, the domain is basically kind of how the topmost layer of a sandboxing. So like app domain means it's an app, camera roll is a camera roll. As you can kind of tell, the names make it plainly clear what domain they live at, but this is the highest level of sandboxing outside of the app sandboxing that exists in iOS. And then the rest of the blob would have basically a data indicating the path, the absolute path, the SHA-1 of the file contents, an encryption key, the mode, and then just a few other Unix file permissions, as well as some properties indicating the name and value. And one important thing to note is that obviously, because they don't want you just being able to pull up a backup and look at it, all the files actually are, with this type of backup, all the files were flatly located at the backup directory level, and they were all just basically files that had one hash as a name. As you can see here, how to calculate that hash would have been the SHA-1 of the domain name followed by the path name. Now, modern iOS, since iOS 10, is actually in a SQLite database, which has two tables, files and properties. But if you look at it, it's basically the exact same of what existed in the manifest MDBD, except it's now just in a SQLite table. So actually now with more relevant, you can see here that you can see the actual hash name, you can see the domain name, and you can actually see the paths of the file. And then basically the flags indicating the type of file, as well as blobs with some data about like if it was a protected file, what kind of protection class it falls under, and some other file information. And on the right here is a screenshot of where on a Mac system, if you actually go to the backup location, you can see that they added a little bit of extra security around it, hoping so that you can see the backup level directory outside of the plist and the database files. It's now a set of folders, and inside those folders are the actual files. The folder contents are just the first two names of the SHA-1 signature. And the SHA-1 signature is the same calculation as before. It's just now that there's an extra level having those first two characters being the folder name. So the question is, how do you get the phone and the computer to talk? I'm sure everyone is quite familiar with that little prompt whenever you connect to a new computer. It's like, do you trust this computer? Trust or don't trust? And you also see that iTunes pops up a message saying, do you trust this device? So that is a system that is actually running on the iPhone called Lockdown D. And it is the Apple service that controls the pairing of a mobile and computer device. A connection to the Lockdown D service is initialized when you make a USB connection to a mobile device, which triggers the USB MUX daemon. And then it checks to see if there is a pairing certificate. I just realized now I didn't give the Windows path. I forgot to retrieve that. But on a Mac, you can find your lockdown certificates at var db lockdown. And then the pairing file is named the UDID of the device, .plist. If that file is found, then it means the device will be syncable. If not, then you get the trust message. So there are two known US UDID calculations. So with a pre-iPhone XR and XS, it used to just be a SHA-1 of the serial number plus the IMEI or the CCID, plus the Wi-Fi, and then the Bluetooth MAC addresses. And then on the iPhone XR and XS, the UDID is actually a padding of zeros, followed by the device's chip, followed by another padding of zeros, followed by the ECID. And then you can see here, actually, looking at this file that I screenshotted the lockdown certificate of, that this was a newer device. This was a iPhone XS that we made, that I used for this example. And this is what a lockdown pairing file looks like. So it has a certificate of a device, information about the host, the root certificate, and then the Wi-Fi MAC address. So now we'll actually start getting into some of the phone data structures itself. So obviously, we're talking about a phone, so we'll talk about the most important aspect of the phone, which is the phone and the FaceTime. So before iOS 8, the phone's database existed at this path, home library call history, database call history.storedata. Actually, no, that's a current path. The previous path was home library call history underscore history.database. After iOS 8, it was the call history.store database. So while the path location changed, the database structure actually really did not. If you had an older jailbroken device or a disk image, you might find sometimes it was also stored within the wireless folder, but that seems to have been something that's stopped over the past few years. I think now they just always keep it at home. I think actually around the time of iOS 8 that changed. And then FaceTime is also tracked through this database, but it's in general, because in general, outside of the video service, FaceTime uses a lot of the same backing services as a phone would use. So therefore, the backing structure is the same, so the database would be identical. So over here now, so this is kind of where we get into the fun stuff. So the top part is the actual table schema of the call history databases. So it consists of, and you can tell looking at this, this is definitely core data. You have Z primary key, you have Z metadata, which is all very known common constructs to any core data SQLite file. So if you ignore this, you basically have about 4 tables we actually care about: call database properties, call record, call handle, and remote participant handles. But the good news is with the phone call, we only really care about call record. So if you look here, this is a SQL query that I wrote up that basically pulled out some of this data from the database. So looking at this, you can kind of see that you'll get the timestamp of when a phone call was made. Since these were all outgoing calls, the was answered is always going to be 0 because we sent out the call, so we don't care about if it was answered or not. I think with these first 3 calls that there was, the phone was never picked up, so there was null. The next 2 calls was disconnected, and then the final one was hung up. You got to see if it was a phone or a FaceTime call. You'll know if a call was incoming or outgoing. You get how long the call lasted, the country code for it, and then it will tell you. And then the service provider is basically a duplication of the call type, and it's giving the Apple product names if it was a telephone call or a FaceTime call. So next is then probably the other biggest table that would deal with a phone function, which is SMS, MMS, and iMessage. So this is a path that's remained static. It's always been at home, library, SMS database. And then the attachments have always been under a giant set of folder structures under the SMS attachments folder. And those folder structures are based off the GUID of the attachment. In my mind, this is always one of the most frustrating databases to deal with, because Apple is always adding something new every release or the other, like Digital Touch. iMessage itself is considered an addition. Emojis. There are quite a few elements that have come in over the years. So being core data, it's quite easy just to bump up the version, you add a new schema, but that means then basically every time you do that, any SQL queries you have break because there's new columns or maybe some columns have reshuffled. So then it always gets a little aggravating. And actually right here, I make a mention So digital touch, when it's stored in something called protobuf. I'll really dig into protobuf a little bit later, but it's a common structure that's developed by Google that was used in a few other places besides SMS, because it's a good way to really compress data, especially image data. So this is what the SMS structure looks like. As you can see, there's quite a few tables, and there's a lot of intermediate join tables, which make it interesting when you have to track across them. So there's attachment, chat, and the message tables, which are the three primary tables, and then there's three joining tables, which help you kind of link the tables together. The rest of these are either syncing related stuff or general SQLite stuff, which is ignored. So actually, if you look at this, it tends to map more towards SQLite than core data, but again, I think some naming conventions can change. There is actually a deleted messages table in here, but traditionally it's not stored in here. Apple usually vacuums out their data as fast as it can. So with this one, I went a little more in depth. As you can see, that's a pretty massively gnarly SQL query just to kind of get readable data outside of it. So with here, you can see the message date, the date it was delivered, and the date it was read. So you can see sometimes they'll be the same, but you can tell in some cases they're different depending on if you got it. You'll see some of these have blank messages because this means they probably have an attachment, which if you look at the second half of the image, you'll see that. So if there's a text assigned to that message, there'll be a text in the message column. They'll have the contact ID here, which can be a phone number, or if you're basically doing iMessage, you might also see the person's iCloud account instead. And then with the service, you'll see if it either comes across SMS or iMessage. You'll see the account that it came from. So this is the account of your phone. So you'll either see your phone number for an SMS or your iCloud account if it's email. You'll get a flag saying that the message was delivered. In most cases, it should be yes. You'll be able to tell if the email was sent or the text was sent or delivered. And if it does have an attachment, it will have the path of the file name here, as well as its MIME type and its short transfer name, as well as how many bytes are in it. So the address book is one of the slightly more interesting, not because it's complex, just because they actually split it into two databases, and it's been like that since the beginning. And it's also interesting, one of the more commonly known core data structures, just because Apple, for some reason, way back when, had made it actually available as kind of like an unlicensed library. A lot of people would link into it and use it, but even though if you used it, usually your app would get thrown out right away for using a private library it's not supposed to. But because of that library, you can actually, it's kind of easier to find documentation about the naming conventions of the address book. It's slightly convoluted because there's a bunch of random tables that contain a bunch of random flags, but not all of them are necessarily needed to get information. And it's definitely not as complex as SMS. So both the databases are located at the same place, home, library, address book, except one is called address book and one is called address book images. Well, I definitely had an address book image associated with one of the contacts for my test example. I just didn't pull the database because there's not much you actually get from it. The database itself is very small. Well, I actually put the schema, I didn't put the query from it. So as you can see here, there's about probably 16 tables that have the AB prefixes, which are the actual core data elements, then as well as 2 in the address book images databases. But predominantly, we really care the most about AB person, AB multi-value, AB group, AB account, and obviously AB full-size image and thumbnail images. The rest are just kind of tables that help coalesce some of the data, but they're not even all needed for a query. So here's the SQL query that would actually pull out a bunch of information about contacts. You can see basically the first and last name of the person in the middle, if you so chose, the organization, any dates about when the contact was created or modified, and then any information about such as a phone number, email, and addresses. And no, those are not my real phone number or not my email. I'm a little more self-aware than that. I think if anyone is a fan of Tommy Two Tone, you hopefully recognize that phone number and the email I just popped out. And obviously you all know where this address is, because if you come in person to one of our meetups, that's where it's usually been. Yeah, but as you can see here, actually, we reduced the number of tables. We didn't even look at AB account. We just looked at AB person, multi-value, and we only looked at multi-value entry and entry key just to actually help us do some more detailed mappings. We could have left it out and done slightly more longhand to relate some of those fields. So photos and videos. Like with SMS, it's kind of a two-part storage. There's a database which is used to actually basically keep the running list of images, as well as its location, maybe EXIF location about the images, tagging, and then the actual physical information, also actual physical images and video also live close by. So predominantly, if it's something's in your camera roll, it will be located at media DCIM 10X Apple. Traditionally, it's 100. I've seen 101, 102, 103 a few times. I think it kind of, there's some values that affect that. I don't exactly know what determines that, but it can exist. And then if it's something that's outside of the camera roll, such as if a memory or a shared photo stream, if you took like a rapid capture or slow-mo capture, the unedited versions of that will also appear just within various folders within media. The database itself is media, photo data, photolite, photos.sqlite. And if you had shared photo streams, there are also additional plists which contain information about the stream, such as the name, the iCloud account the stream is associated to, and even other people who are in that photo stream, as well as if they've joined, if they haven't joined, if they're the host or not. Photos is a database that's actually really large. There's a lot of random tables that's lying around because a lot of the iCloud syncing stuff, which is the case of some of the other tables. But only about 5 or 6 tables really are queried for some of the information that you needed. And this is the dump out of the tables. That's, again, very large. But I think in reality, what you really care about for just most photos and videos themselves is Z generic album and Z generic asset. You might pull in things like Z detected face if you have moments, Z cloud if you have any shared stuff, any of the Z cloud items, Z memory and Z moments if you have moments albums, and Z persons if you've actually been able to tag people in those. So actually this query is so massive I didn't list the entire query. As you can see here, you can kind of see if the photo was saved from a random source, like maybe if you saved it from a text message, if it was from a photo stream, or if you made it on this device, you can see what directory it resides in, the name of the file. Maybe if you copied it from somewhere else, it might have a different file name. You'll have the UTI type and some information letting you know if you actually tried to download it or anything. And also letting you know if you favorited this image or video or if you modified it. And then for a reference down here on the right, this is kind of what the DCIM folder actually looks like, and you can see DCIM 100 Apple and then list of list of photos from the test device. And since this was a smaller one, there wasn't any photo streams or anything. I didn't set any of those up because I thought that was a little too advanced and outside of the scope maybe for what I wanted to get to for just a quick primer on digital forensics. And then there's some other stuff in media, some of which I'll cover later, some of which is not as relevant to forensics interest, but I'll get to some of that a little bit later. So next up, calendars and reminders. So while calendars and the reminders and the task lists are actually two completely separate apps on your iPhone, they share a database. It's only one database for both those applications. And it's located at library calendar SQLite.database. And it also stores information about like your clock alarms, if you've gotten any notifications about your calendars. It has separate events about recurring events. It has separate information about that. If your calendar events had any attachments, it also has references to those as well. And as with most things Apple, there's a lot of superfluous tables, predominant amount of table that's kept to 5 or 6 tables for relevant information. So for a calendar, the two primary tables are calendar and calendar item. So again, you might find some interesting information in alarm and recurrence about when you'll get a notification about when a calendar item is going to occur or how many times the calendar is going to recur. And you can see here so that, oh, so look at the very top of this query I listed, you can see that the DC iOS meetup is happening now. And it's not an all-day event. It was on the home calendar. And then the rest of this was one of the default pre-filled US holiday calendars. So maps is something that's also been relatively much of a pain, and it's always been a known pain. So the iOS, in one of these rare, interesting times, the iOS system default maps was Google Maps when the iPhone first came out until about iOS 6 came out, at which point that they finally had the schism. Apple got their own map solution built up instead, so we switched to Apple Maps. However, the Google Maps on the system through iOS 6 and Apple Maps have had to use the same data format and storage. Google Maps, which is a third-party app, has a completely different storage and backing system. However, Maps has also become more complex because starting with around iOS 10 or 11, if an iCloud account was actually synced to the device, then you would not get it in a backup. It just would not be there. You could only retrieve it if you had a disk image or a jailbroken device, or if you disconnected the iCloud account, then it would actually show up in the backup. It would be stored in a file called geohistory.maps data. However, I actually couldn't even find it when I did my research for this, so maybe they've even tightened it down more. Now it just is not stored on the device in general anymore. That would be an interesting change, but it's possibly something that happens. So, and then, as I said, they share the same data format, and I mentioned this earlier, so this is kind of where I'll dig into it now. Maps is basically a plist that's compressed using the Google Protocol Buffer or protobuf storage mechanism for compression and transport. When you uncompress it, it looks kind of like a plist file, but otherwise it's this complicated data structure that's all really just a bunch of binary blobs that makes it easier to send massive amounts of data over a smaller byte stream, which means you save data. Side note, it is only because of Apple Maps I ever learned that Objective-C++ was a thing and how to use it. And I don't think anyone probably even really knows what Objective-C++ is anymore because Swift kind of has no need for that, though that's a separate topic and a separate subject. So one of my slightly more favorite subjects we'll talk about is notes. So notes, again, like a lot of these with these schisms of more evolutions of iCloud and more advanced data structures, has two locations. iOS notes before iOS 8 were stored in the home library notes SQLite file, while after iOS 8, they were stored in the note store SQLite file, which was found within the actual sandbox container of the Notes app. So that location would depend if you had a backup, if you had a full disk image, because they were two kind of separate locations because of the obfuscation that goes on when you look out at the disk image versus what a backup needs. So if you had a backup, you'd actually have like the COM Apple Notes folder, so you would know that. But with a disk image, it's the more abstracted GUID. And then along with the note bodies, you also have any images and sketches that are stored within the hosting folder of the Align database. And then the notes body is actually now stored as a gzip compressed protobuf blob, because again, you're going to have a lot of raw HTML text. You'll have like list formatting. You'll have all the indents. You'll have images. You'll have sketches. So again, this is all compressed down using protobuf and then can be re-expanded. The protobuf mainly is for like more of definitely the images. You can kind of reconstruct a lot of it using just by ungzipping it. And iOS 9.3 added what's probably one of the more interesting wrinkles, which is that you can actually encrypt your notes. This was more of a local encryption because it wasn't tied directly to your iCloud or any other passwords. You have to basically input to create a password on a note-by-note basis. And all parts of the note would share the same key. So like if you said the same password for the note, it would then propagate it for the notes, attachments, and metadata. But they would have separate initialization vectors and tags. And the encryption standard for this is the AES GCM standard, and that's about all I will go into on this subject. So as you can see here, this is kind of what the note database structure looks like. There's only really two things that are looked at in this database, which is the iCloud syncing object and the IC note data. The rest of this kind of is not needed. You basically will construct a note from the note data and the syncing object. And this is a table that kind of this is a database that joins in on itself a few times because you have to kind of relate each row and syncing object to the note data, to any of its attachments. Then you can see here, this is what the application folder looked like for notes. So you'll see that it has fallback images in the media because that way, for some reason, it's a weird double standard with the backup because you can actually get all the images without needing the gzip protobuf. You just won't know how it relates to it. And then, so here's the example of notes that I have. Again, I kind of showed both columns because this one has more interesting stuff if you expand across. So as you see here, you'll have the blob. You'll have an attachment data. It's null unless there is attachment data, which is also then a gzip blob. And actually you can tell, so like this is actually like a table within the HTML. This is a drawing. This one's a JPEG, but since it's an external image, it's actually not residing in the blob. You'll have information about the notes. You'll get a quick snippet of the note. Interesting fact here, 5 and 6 are actually the same note, but 5 is basically a discarded trash version of the note before it was encrypted. So technically, the database is keeping some things around that aren't encrypted. It just depends on when you look at it. It might eventually disappear. And then over here, you'll kind of see that this is the encrypted one. So you see there's a password hint. In this case, it may or may not have been the password, just for an ease of demonstration. You'll see how many times it was wrapped. And then you also see the, you also have the blobs for the key, the IV, the salt, and the tag. As well as you get when the note was created, last viewed, last modified, the folder name, as well as what the full folder ID is. I think my math was a little off on the viewed. There's some discrepancy. As you know, with Apple, sometimes they adhere to the regular Unix epoch. Sometimes they have the references to their own date instead, which is the 1/1/2001 date. And once in a while, there's just a random one that doesn't match to anything there for some reason. So as you can see here, theoretically, you could go around with all this information and technically try to brute force a node open. It would just take, again, a long time depending on how simple or complex the password is, because the key is stored wrapped. So you still have to unwrap the key in order for it to be used. But theoretically, you have almost all the parts right there. So email is one of the more safer aspects, probably, because you can only ever get an email from a jailbroken device or a disk image. It's not even stored in encrypted backups. So it's located at home library mail. It consists of 3 main files: the envelope index, which is the databases for all the mailboxes, as well as metadata relating to the mailboxes. And then there's the protected index, which is the database for the actual mail messages itself. So mail is actually like a 2-step process because you have to get the information from the envelope index and then relate it to the protected index. And then there's also the P list, which is just a list of all the marked VIP contacts that you might have indicated. And these are the table structures. I actually don't have any emails on this device that I use because, again, I'm not predominantly an iPhone user, and I'll get a little more about the device I use at the end for most of this. But the top here is the envelope index, and the bottom is the protected index. As you can see, the protected index is a lot smaller because all it has is the individual message data, while the envelope index has more of the references to all the messages. So Safari has its information spread over 4 databases: bookmarks, browser state, cloud tabs, and history. Cloud tabs is a newer database. I never really interacted with it much because I hadn't seen it before this research, so I'm kind of going to ignore that one. I'm assuming it's predominantly dealing with synced cloud tabs if you've been looking at something on your Mac and you go back to your phone and it's there. So otherwise, these databases kind of speak for themselves. Bookmarks stores all your bookmarks. Browser state has all the list of your open tabs, private and non-private. So obviously, you'll usually only see one private tab at a time. And then also just the history of your Safari if you haven't cleared it, but that's only your public data. The private data is not recorded there. So So at the top is your bookmark database. You'll see very small table. You only even need to look at the bookmarks table, and it pops out everything you need. The history is also a small table, and again, a small database, and again, you only need one table, the tabs table. And you can see it lists the title of the page or URL when you open the tab, as well as if it was private or not private. And then finally, the history. History involves a little more things to look at. You probably need to look at history visits, history items. But again, it's a slightly less complex join, and then you got to see when you visited pages, how many times you visited it, as well as where you visited it from. So audio recordings and voicemail, they're semi-related. I kind of lump them together because they're both smaller things. There's not as much data really on them. So recordings, as you might have seen earlier, they're kept at the media recordings folder. And the data is either in recordings or cloud recordings.database. Again, cloud recordings is something new I found doing this. And then all the recordings, excuse me, are stored at that directory based off the timestamp. And voicemails are located at home library voicemail database. And the AMR files are just listed there as a sequential number and are stored in the same folder as the database. So yeah, I kind of mushed this slide a little bit together. So at the top is the database structure for the cloud recordings, as well as the information. So you'll see at the date, how long a recording was, if you gave it a name and location to its path and its unique ID. And again, this is where it resides in the file structure. And then here is the voicemail table over here. And it is literally, the voicemail database is literally one table. So that's why I expanded it out so you can see all the columns in it, because it is only one table. So the keyboard is now only retrievable through disk images and encrypted backups. It used to be available in regular backups, and that kind of stopped happening. And also Smart Prediction kind of changed how this worked a little bit. But if it's on, then you would find it either at library keyboard star dynamic.dat, where the star would be the specified language. And then also there may or may not be a library keyboard dynamic text.dat file. But this is really simple because it's not even a database, it's just a hex file. So if you look down here, it's just a hex file. You get the version of the dynamic dictionary version. Last I checked, 5 was the latest version. And then you just get the list of files, list of known words. And this is basically your autocorrect list. So if you start typing something and you get a pop-up in autocorrect, it's because it's here in dynamic text.dat. So location has definitely been one of the more controversial ones in Apple's subject. About iOS 4 is when people actually discovered, oh, my iPhone is actually locating and knowing where I've been. And there's kind of a huge brouhaha about it. There was some white papers about it back in the day. I tried to see if I could find any of the important ones, but I wasn't able to. I think Jonathan Zidziarski had a big white paper about it. I couldn't find that one though, unfortunately, but he's a big name in iOS forensics. So if you look around, he has a lot of subject matter expertise. The good thing is location data can't be found in a backup. And I think that only used to be, you could only find it in a backup up to 4. After 4, it was only basically on a disk image. And this actually I mistyped this one. So I think I broke my own naming convention. See, it's not even, it's found in private var root, caches location D with a cache encrypted database. The name throws you off, it's not actually encrypted, as well as in a consolidated database. And additionally, if you have frequent locations, and you have that service on and you kind of go to a lot of locations, there's some caches there that actually will also say, I've been to these locations a lot, and it tracks all that. So this is what the location database looks like. This is cache encrypted B.database. Sometimes it might be A, but usually it's A or B, not C. And you can kind of see they've really kind of went overboard, because you can have a CDMA, which is the older Verizon standard, cell, which I think was more the AT&T standard, LTE, and then Wi-Fi location. And then here I kind of just did a dump out of the Wi-Fi locations, showing when at this time, these are the coordinates, the MAC address or the Wi-Fi address it found, and just some general other approximation information it put. So what's in your wallet? Okay, I had to make that joke. I'm sorry. So Wallet actually evolved from Passbook. So it's stored at library passes 23.SQLite, but it's only findable from a jailbroken device or a disk dump. I don't think you find it in a backup anymore. Initially, Passbook wasn't really cared about as much because you're only storing maybe like your Starbucks reward or a few other things. Once like flight tickets started getting added, it became a little more interesting. However, I think it really probably picked up popularity once credit cards were added, and then Passbook evolved into Apple Wallet. I'll admit I didn't play as much with this personally because really Apple Pay came out after I left this line of work and I came over here, so I think it wasn't as popularized. So, and actually I didn't have any data over this, so my example data screenshot will be from a presentation from another known forensics expert, Sarah Edwards. Her resources are also linked to the resources slide, but she actually teaches some of the SANS courses, and all her stuff's very publicly open on GitHub. My surprise was this database changed a lot since the last time I looked at it. It's actually now 86 tables long. And I honestly think a lot of that's just for obfuscation because there are some weird named tables. So if you go look at it, there's tables like avocados and bananas and bacon and blueberries. I'm guessing Apple just has some interesting code names for things. As you can see, there's a few kind of relevant tables hidden there, like location, location index, payment application, payment message. Now, I hadn't seen this before I looked at Sarah Edwards' research in one of the presentations she gave about a year ago. So one of the things actually can do is if you use Apple Pay, it actually kind of shows, hey, this is the card and this is where it's been used and what I did with it. So this was kind of something that was interesting. So I'm curious to see how, because this was given out a year ago, so who knows, maybe if this has changed since then, but I thought that was an interesting find that, again, your phone knows. And then finally, one of the biggest things we talk about is just third-party apps. In general, it's really up to the app writers and app developers to make the protections for you. You can't really control what the backup does. So this is why, you have NS file protection classes, and you do things like making sure data stays on the device or can only be used once the device is unlocked, because otherwise it will show up in your backup. Now, if you have a disk image, it doesn't matter because most of the stuff will be there anyway, but even with the disk image, you can protect a lot of this, and a lot of the stuff won't be visible, but you'll get a little more than if you looked at the backup. Again, as I said earlier, it's easier to find data from a backup because then in order to help iTunes reconcile it, it actually has to give it the full package name. But if you look at it from a backup, then you actually have the full data application path with the app's GUID, and then you kind of have to play a game of cat and mouse to find what you want. And a lot of the common third-party apps are usually well analyzed, and people have written a lot of parser to extract data from these. So we're actually now starting to come up on the end. So this is just the tip of the iceberg. This is the main Apple apps that can be looked at. Other serious forensics researchers have looked and found multiple other sources of data. One big thing is like the health kit. There's a lot of stuff that can be gleaned from that. And that's one thing you can only get from a full disk device or an encrypted backup. So again, there's kind of these trade-offs of what you can get and what you can find. The phone is a treasure trove of information. It just depends on how much time you want to spend searching. But also, it's okay to relax. It might seem terrifying that your phone knows this much about you. But again, the only people really interacting with your phone are you and your phone. Pretty much all of these require someone really to be able to sit down, take the time to connect to your phone and break into it. And so unless for some reason you've ended up on the wrong side of something, no one's probably going to be trying to go dig around your phone and get access to it. And you can't really SSH into a phone unless you jailbreak it and improperly configure it. But that's a different story, and the TLDR for that is if you jailbreak your phone, change your SSH password. And this is the list of resources that I had besides my own knowledge, like Sarah Edwards' blog, SANS, Ziarski, the iPhone wiki, which was basically like used to be the old coalition of jailbreakers, the Buy Mobile Device, which is a third-party library that allows you to do the iTunes-related stuff from the command line. And that's all I've got. Any questions? I know I saw one. So let me go back over to a chat. All right, Jay. Yeah, so regarding lockdown, yeah, the phone does have to do a new key appear for each time it's connected to a new computer. And I don't think the phone itself actually stores the connection records. It's up to the computers to host connection records. I think that's kind of done for like a secure, like a safety perspective. So that way you don't know what phones you've been looking at. It's up to the computer to make the connection to the phone. Yeah, screen time beta J is covered. I don't know too much about that. I didn't list it yet, but if you look at Sarah Edwards' stuff, she actually has a lot of documented stuff about screen time. Yeah, that stuff is also capturable. Um, so I don't think I don't know if there's a real way to get the password for a backup. If you don't have it, you don't have it. You could theoretically, I think there is one way, but basically it does involve a jailbroken device because you basically have to have the device, be able to access the hardware and get like the hardware key. And then from that, you can start doing some of the unwrapping, but it's a long and tedious process. And I think forensically, you wouldn't see the timeouts because you're probably trying to access it programmatically or not through iTunes or something. So you might not see any issues with timeout just because you're probably trying to brute force it through a way or connect through a way that's not iTunes. So I don't know if there's any sort of timeout issue. It's just obviously if you keep brute forcing it, it's going to take a long time. I don't have any direct resources, Jay. I'm sure you and I will talk offline about this. I'm sure I could dig some up. And again, I think if you just start searching around, like a lot of the forensics experts like Edwards, Heather Mihalik, they've commonly done this. I definitely have a textbook that I have. It's digital though, so I don't know if I can share it. Like, I don't know if I can share it, but like at least as of iOS 9, it had some data structures around some of the more common apps like Facebook, WhatsApp. So I think it's kind of you just got to Google hunt and see. But I think, so the Mac Forensics, which is Sarah Edwards, is if you link there, it would link to her GitHub, and she might have some queries and stuff for looking at some of those apps. Okay. All right. Well, that question I think accidentally came to me privately, but so Bob asked me about Sarah Edwards' Apollo script and how was it useful for me, and so people know if you go look at her GitHub, there's this public repository. It's basically like a parser condenser that basically goes through a bunch of the databases and then dumps it out and then into one single database for you kind of the query and search through. I found it a little helpful. It would help me do a little bit of this. It helped me generate some of my own SQL queries because it's been a while before I looked at some of that stuff. But overall, it didn't help me too much because it didn't cover a lot of the databases I wanted to look at. It helped me with SMS and Safari a little bit and call history. A lot of the other stuff I had to do manually and redo on my own. I'm sure theoretically I could always go and make contributions to our modules that cover some of these, but I think hers looks more at timelines, while mine was, for this case, was looking more at raw data. Actually, and yeah, if anyone else has questions, you can try or raising your hand, and we can unmute you. And then if you have a microphone, and then you can actually ask your question too. And I'll put video back on while I'm answering questions, so again, people can see me. All right. Have any of the recent sort of low-level jailbreaks been useful in your forensics? So I didn't use it in mine, actually, so that was a very big call out. Thank you to Jay Tamboli for allowing me to borrow his jailbroken device, because I don't own any, again, iPhones. So thank you for letting me to borrow that to do some of my extraction. So checkrain has the possibility to be forensically important. I'm not going to go into why, kind of because it crosses into my previous line of work, but a lot of the jailbreaks are only good for getting into forensics, but checkrain has some applications that could be used, but I'm not going to go into why. But yeah, low level is considered helpful forensically. All right, so John Whitmore asked, when jailbreakers talk about saving your blobs, does that match up to what you're talking about? No. So that is a reference to some of the older stuff with jailbreaking. So there's the blobs in that case actually refers to the Apple update data, the SSH package. Because basically, if you nuked your phone and you had to revert, if you didn't have the SSH blob for that app version, you couldn't restore that version. You'd be forced to update to Apple's newest version. So for jailbreakers and forensics people, it's important to have those blobs, because if for some reason you mucked the device and you reset it and you had to update, you would need some sort of SSH blob to point to a specific version instead of, and to intercept Apple's server, because otherwise, even if you had the right restore IPSW, Apple's server would reject it because it wouldn't be valid anymore. All right, I'll do one more ask for any other questions. If not, then thank you everybody for coming. If you have any other questions, hopefully we'll be able to address them next time. We are planning to meet next month. I think we will still figure out what exactly our speaker situation will be, so just keep apprised of the meetup page. I assume we will be virtual again for next month. And if you have any questions, feel free just to reach out to us on Twitter. All right, thank you.